Welcome to my new calculus channel. My name is John Gabriel. In this video I'd like to discuss the first ever constructive proof of the mean value theorem. Now it's important for you to realize that before me no academic was able to prove the mean value theorem conclusively. They would actually attempt to prove it using a little geometric sketch with a line parallel to the tangent, but that wasn't a conclusive proof, and it wasn't even a proper proof because there are errors in most of those proofs. In fact, in all of them as far as I know. So what I'd like to show you today is a systematic constructive proof, and I will do that using the standard calculus, the apparatus of the standard calculus, but I need to introduce a little patch I created because the mainstream calculus is so broken that it's not possible to have a constructive proof of the mean value theorem without my patch. I don't know if any of you have ever read the entry for the mean value theorem in the Encyclopedia Britannica, where it states that very deep properties of the real numbers and understanding of foundational mathematics is required in order to prove the mean value theorem. Well, that entry is false, and it's false for many reasons, but one of the reasons that stands out is the very fact that real numbers do not exist. So aside from that, the mainstream formulation of calculus is heavily flawed with lots of self-referential definitions, wrong concepts, and a lot of confusion that is sown by the most unbelievably stupid people who are in mainstream academia. Okay, so what is the purpose? The purpose is to explain why the mean value theorem works. So let's see the statement: if f is continuous on that closed interval x and x to x plus omega, where x is less than x plus omega, and smooth on the open interval x to x plus omega again, then there exists a point C such that the derivative at C is equal to the ratio of f of x plus omega minus f of x to omega. So to make this work, let's define the derivative as follows. Now, omega in this particular formula is actually the length of the interval. So a lot of you know where Newton introduced the distance h from the point. Well, omega is the same as h. So what I do is I divide omega or h into n equal parts, okay? And then I define the derivative as you see in the formula nd. You can actually try that out. It looks different to the standard formula, but it's more reliable because the denominator in this particular formula is never zero. Incidentally, I discovered this when I was still in my teens. I was trying to fix up the broken calculus, and this is one of the formulas that can be used without actually ever saying that there is a division by zero. Okay, but still there are a lot of problems with it also, which I'm not going to go into here. I've done that in other videos and you can check them out. So using this definition then, we can define any of the positional derivatives at a particular point. When I say positional derivative, I mean at any given location on the curve. So if, for example, the point is in this interval, right, then the positional derivative is defined like this, as you see in the formula PD. Right? You can actually try this out, and it works. With one caveat, you cannot really evaluate a positional derivative. in terms of its actual numeric value, all you get is a generic derivative. Okay, so it's only a generic derivative, but that's all we really need to show the constructive proof. So if we assume that the left-hand side of the MVT is an arithmetic mean of all the ordinates of the derivative of f in that interval. So let's see that again. F dash of c, or f prime of c, the derivative at c, is an arithmetic mean of all the ordinates in this interval here, right? And as n gets very large, it gets closer and closer to that derivative. So let's start off now with the right hand side and show that it reduces to the left hand side. In other words, a very easy, straightforward constructive proof, right? Alright, so we begin with the right hand side. So we say down here where you see the limit as n approaches infinity or tends to get very large of this particular sum, then we can replace each of these ordinates with their corresponding values or subscripts, so to speak. And now in the next step we replace each of these positional derivatives. Remember, you can't evaluate anything in between the first and the last one because they're all positional derivatives. They're really symbolic of all the derivatives in the interval. Obviously it's impossible to find the arithmetic mean if one were expected to actually do it in the way that it's described in the formula SD. But we'll see that the fact that a telescoping sum exists actually makes it possible to do exactly that. So in this case, those who love the concept of infinity will go, but you can do it because of the telescoping sum. Well, you can't really do it. The telescoping sum is just a property that makes it possible to do, but it's not done as a super task. Okay, so this arithmetic mean is never a super task. You don't actually go through and add all these up. But you'll see that all the terms between the first and the last cancel out, as we'll see now. So over here we have the entire sum that we saw early on, and we replace each of those derivatives, okay, each of these derivatives here, with the definition. All I've done here is I've taken out w over n and put it in front of the bracket, and you'll see that everything between the first and the last terms cancels. So this is positive here, this is negative, this is positive blue, negative blue, and so on. So that right at the end, all you have left is the last term, the difference of the last term and the first term, and the n's cancel out here, and all you have is this expression here over omega. And since n is no longer a factor, we just simply drop the limits and we have the desired result. Now, you may say, well, that doesn't look exactly like the standard definition. Well, that's pretty easy to fix. All we do is we replace x by a and we let omega equal to b minus a to arrive at the ubiquitous form, which is f prime of c is equal to that particular ratio, okay? Now, that is the constructive proof in just 3 pages using the bogus calculus. So I'm using Newton's and Leibniz's and Cauchy's bogus calculus. This can also be done using the new calculus in a much simpler way by using the new calculus definition of derivative and considering an interval like I've described here in this diagram, and finally doing the same thing as we did in the mainstream calculus, but with no patches, no kludges. All of this is sound, rigorous, and we arrive at the same result without any ill-formed concepts such as infinity and infinitesimals and the theory of limits, which requires that real numbers exist. So that's these are the two different proofs. And if you're Chinese, you may want to look at the Chinese version. This was translated by one of my students, and so this is the Chinese version of the mean value theorem, and there you have it. And I will place links to all these articles. They're actually available on my Google Drive. This is the first ever constructive proof of the mean value theorem in human history. Okay, I, John Gabriel, am the first to do this. None of the morons who came before me even dreamt about it. In fact, they've never understood the mean value theorem. Also, they've never understood that from the mean value theorem you get the fundamental theorem of calculus in exactly one step. None of the moron academics in today's academia understand this. I am the first and the only person to discover this. Anything that they've learned about this, they've learned from me. This is old knowledge. I have a lot of other knowledge which I haven't shared because I have been persecuted, and which I don't plan to share. But what would really be amazing is if I could come back in 50 years' time and see how far these morons have progressed, because I was able to do this in a certain amount of time, and I doubt that they will even get halfway to the point where I have gotten. So the penalty for persecuting me and calling me a crank is that you fucking morons will not get to know any more from me. Okay, that is a penalty. I hate mainstream academics with an absolute profound hatred, and I can't even begin to express my disdain for these dogs. I'm thinking of people like Professor Gilbert Strang, who's a bloody homosexual and a pedophile and a moron on top of it. And then I'm thinking of his lackey, Dan Christensen, on Sci.Math, who is an unbelievably vile, despicable, filthy human being who doesn't even deserve to live. Let me give some more credits. The vile bastards, Professor Jack Hazinga, Professor David Joyce, Professor David Ulrich, and that cunt from Good Math and Bad Math, Mark Duperol. I piss and shit on the lot of you. I hope that even after I'm gone, students will see this and somebody will have the patience to deal with you fucking morons, because I don't. I am done with you. I will just ridicule you. I have nothing but total contempt for you. I would literally want to see you dead, if possible. That's how much I hate your guts. Okay, so take that, you fucking morons. To the rest of you who are watching this video, sorry that I blew up like that. I have a lot of pent-up anger because I've been called a crank a long time, and I'm the only one who's really not a crank, and everybody else is a crank. So there you have it. Shouldn't have blown up like that, but I'm extremely angry. I hope everyone who has said a bad word against me dies a horrible, miserable death, because they're liars, they're deceits, they're jealous of me, they have never accomplished anything in their life's journey, they don't know any mathematics, and they're going nowhere. So that's the reason why I am upset the way I am. But I hope you've learned something from this particular video. The fact that the mean value theorem is nothing like what they teach you at school or university. It's something completely different, and no one else except I really understands it. But hopefully now you will understand it too. This is the New Calculus channel. I am John Gabriel. Goodbye.